right, so at this point, I am pulling up the wheel, and I am hitting record so that the lesson will post in the weekend. I'll post it on Sunday. But let's go ahead and get started with the spinner. It looks like everybody, at least who asked me today, had the mark. So fingers crossed.
Please, if it's dark orange. It's not dark. It's dark orange.
Let's see who do we have today.
Please, dark orange.
Victoria. So Victoria, let's see. Victoria did not ask me though. See if you got it.
Please.
Okay, so 4. Right. So we are gonna go ahead and go over the answers though. Especially that 5th one, we had varying results. If you get the point next class, that does mean you get donuts soon. Because you are at 11 and you need to be at 12 to get around with donuts. So let's go ahead and get started. Luke, come on up. And we're going to go over the answers first, and then we'll get to today's lesson. Today's lesson is an important one. It is a heavily tested lesson, and it is about how much energy is available for a chemical reaction to take place. We need to know this in order to predict if a reaction is being spontaneous or not. Like to further clarify whether the reaction will happen. So, first, what is entropy? It's number of possible arrangements.
Are you going to keep it forever? I'll bring it back. You want me to keep it forever?
Of particles. So you do have to say of particles and their energy in a system. And I do believe you have to say that too. They used to accept just a measure of disorder, which is how I learned entropy, but they're a little bit more careful as of the 2025 syllabus with the definition. And definitions they're really strict on. I got a couple of the paper 2 spec that I'm reviewing from Cambridge, and they're really strict on the definitions. So if it is defined, it means you use word for word, whatever it says in the syllabus. If you're missing the key words, what they deem are the key words, then you just don't get that mark. Yes, Isabella.
You have to mention the energy.
So in the older syllabus, it didn't mention that, but the new syllabus does, so I think you do. Yeah.
I understand what that means.
So their energy would have to do with how much entropy there is. If there's more energy, there's more entropy. So I'm pretty sure that that's why they're including that as a factor. So place one tick in this. I think everybody that I checked got this one correct. That means we understand the idea of entropy. NaCl dissolving in water makes aqueous solution. You're going from solid to aqueous. This means that you have more entropy. Delta S is positive. Here, water going to ice. You're going to a more ordered state or less disordered state. So this delta S is negative. You had to get both ticks correct for 1 mark. This right here is the math. Everybody seemed to do the math correct as well. From what I had seen, I had not checked any incorrect answers here. So the answer was negative 514.4. If you did not get that, I can show you at the end of class my work on how I got that answer, but every single person that I checked did get that answer. You are supposed to do products minus reactants and consider how many moles of each product or reactant that you have. Don't want to spend too long on that one. But we will see this again in today's lesson for delta H. And then this one was the one I did want to talk about because this is where if you missed the mark, you might have missed a mark here. Not because you didn't get the sign is negative. And so if you had said negative, that's correct. The idea is that you were supposed to look at the synthesis reaction, which they don't give you. They tell you that it's synthesized from its elements. So you're supposed to come up with the synthesis reaction. You didn't have to write it down. You could, have it in your head. But you needed to have the synthesis reaction, which is this, goes to CaF2. And then all you had to say for the mark and what you should have said is that there is a reduction in the amount of gas. So if you said any reduction in gas molecules. So if you had said anything like there's 1 mole of gas on the reactant side, there's no moles of gas on the product side, that's the same thing as saying there's a reduction of gas molecules. If you only talked about there being a gas, that's not enough information. You have to talk about what you started with and what you ended with. So and some people said that, you went from having a gas to just having a solid, that would count as saying that you have a reduction in gas molecules. So there were a lot of answers that could be accepted here, but there were some that couldn't. You had to make the comparison to say that you went from having gas to only having solid. So be careful with your wording here. All right, so today we are moving on to the final topic in enthalpy. And so remember that this unit 2, was all about enthalpy changes. We started with lattice enthalpy. Then we went to enthalpy of solution. Then we went to enthalpy of titration. We had all the triangles, and now we've got the last one, final boss, as they say, Gibbs free energy. This one is extremely important because it is what describes to us whether a reaction is going to be spontaneous or not. Instead of you just guessing, we have data that can tell us through experimentation whether a reaction is going to happen or not. Do me a favor at the beginning of the lesson, make sure you have your headphones out, just as a regular courtesy on a daily basis. Yes.
You are recording, right?
I am recording, but I'll double check because anxiety. Yes, it does say it's recording. All right, so delta G, this is whether a reaction is going to happen or not. So what is delta G? First of all, we're going to have to state and use the Gibbs energy equation. What does it mean by state? That literally means they could give you a mark for saying, what is the Gibbs free energy equation? And then you write delta G equals delta H minus T delta S, and they give you a point just for that. It also means they want you to memorize this, because one of the places in AS chemistry where they use the subjective state and use was PV equals nRT. You need to know that in your head. This one you also need to know in your brain. Yes, Atzel.
Is that machine thing in the background making noise?
That is the 3D printer.
It sounds like a plane terminal or something.
It's a machine. How long does that print?
30 minutes ago?
Okay, so don't print anything after that. The second one, perform calculations using this equation. So that means we are going to need this to solve questions. So delta G, we said that's going to tell us whether a reaction happens or not. It's actually comprised of 2 different factors. It's comprised of the enthalpy factor and the entropy factor for a reaction. And we'll be looking and analyzing each of those factors. What do they mean? What does nature prefer? In order to tell us whether a reaction is going to happen or not. So now it says state whether a reaction will be feasible. Feasible means, does it happen? That is our chemistry science word for does it happen, will it happen, can this happen? We use the word feasible or feasibility. So will it be feasible using the sign of delta G? Uh-oh, more signs, more positives and negatives to make predictions. We had signs for delta H, right? Endothermic, exothermic. Last class we learned signs of entropy, positive and negative entropy. Today we're doing signs of delta G. So try not to get lost in the signs. And then finally, predict the effect of temperature change. So if I raise the temperature or lower the temperature of a reaction, will it cause a reaction to happen that wouldn't otherwise happen? Or will it make a reaction that would otherwise happen at room temperature no longer happen? Or is there nothing we can do to the temperature to change the outcome of that reaction? There are some reactions that there's nothing you can do to change the temperature. That reaction is either going to happen or it's not going to happen. So we'll be looking at the factors that come into play there. So 4 objectives today. That's what I call the Goldilocks zone. Not too few, not too many. It means the lesson isn't considered to be too difficult or too easy. When you see like 20 objectives, that means that you're getting thrown a ton of content because the content itself is all easy, but it's a ton. What area of the class do you think that happens in? It's not happening here. What area do you think you're going to get a ton of objectives in one lesson? Go ahead, Axel.
Organic stuff?
Organic stuff. When you get to organic, that's where all the like blocks of objectives are. So that's where more of the like, just knowledge base, putting those reactions together is. This is less because you have math and math takes time to analyze. All right, so reminder or review. Do you remember how to calculate delta H? Because you will have to possibly calculate delta H of reactions from delta HF values. Do you remember how to do that? From ASChem?
Probably find the reaction stress.
Delta H, and the good news, delta HR, if I have enthalpies of formation, is it's the same thing we just did last class, but instead of for delta S values, we do it for delta H values. So the enthalpy of reaction is the addition of your delta HF of your products minus the addition of your delta HFs of your reactants. So products minus reactants. This whole area of delta G, everything is products minus reactants. There's no reverse. It's all products minus reactants. So you hopefully won't get confused with it. So then that being said, go ahead and postulate this. I think you could do it. You've got some data. I printed out 2 per slide for you because when I looked at 4 per slide, it was a little bit too small. So I printed it out 2 per slide for you. So go ahead and see if you can get this number. I'll have you start in advance of me. Where is the thing for O2? Let's re-ask that question to everyone.
It's 0.
It's 0. Why is it 0? All elements in standard state are 0. This is the big difference between delta H and delta S. Oxygen has an entropy value in its standard state because it's moving. Is that the... No, it's not. I was like, is that the one that told me to record? It's a little late. Delta HF equals 0, all elements in their standard states. So given that, we now remember that oxygen is 0, right? What is the overall delta H for this reaction? I'll go ahead and start putting down numbers. For my reactant, I got negative 302.9. For my product, I got negative 157.3 plus 2 times 33.2. Then for my delta HR, I did negative 90.9 minus negative 302.9. Sign changes, right? Did you get positive 212?
Yep. Yep.
Yes. What does that mean? What does positive 212 mean? This reaction is endothermic, which means it requires an input of energy for this reaction to occur. What about the entropy of this reaction? Do we think this has positive entropy or negative entropy? It has positive entropy. So although it requires energy for the reaction to happen, it is favored in its entropy factor to happen because what you're making at the end is gases. So what you're going to see later on in today's lesson is an interplay between the 2 factors of enthalpy and entropy. And you're going to see which factor outweighs the other. Is the enthalpy factor the one that outweighs and then the reaction does or doesn't happen? Or is the entropy factor the one that outweighs? But the way you find delta H is the same way that you find delta S. Now, in today's questions, like this easy, you'll be provided all the delta H values as we go through the questions. But on a Cambridge exam, could they ask you to find the delta H first from delta HF values and then ask you to go find delta G from there? They sure could. Very exciting. All right, so entropy and equilibrium reactions. This is a link between entropy and equilibrium. This is actually not in the standard, but going over this helps you understand a little bit about what's going on later on in the lesson. So therefore, you do not need to memorize this equation for Cambridge. If you looked at the first standards, it's not there. But it does give us some important information. When we are at chemical equilibrium, what that means is we are at the point where we are making products at the same rate that we are making reactants. Same ideas apply to entropy as equilibrium, which means the entropy change of the forward reaction will be equal to the entropy change of the backward reaction. So we say that when we are at equilibrium, the overall enthalpy change from now on is 0 at equilibrium. So at 0, so when we are at equilibrium, we say delta G equals 0, meaning that there's no additional energy needed, there's no additional energy being given out. You have just exactly what you need for that to continue going on. This is going to become a factor later in today's lesson. I'll tell you when we circle back to this. But the idea is that just like equilibrium no longer changes once you've reached it, you have no more change in your amount of reactants or your amount of products. The entropy will also be, the entropy change will also be 0. Delta S will be 0. Change that to delta S. This leads to an equation that links the spontaneity of a reaction to the equilibrium constant. And so only if you're studying for the Olympiad would you need to be aware of utilizing this equation, the link for spontaneous reactions and the equilibrium constant. And the formula is delta G equals negative RT ln K. This is actually, and you can look into it, but I believe that it can be derived from PV equals nRT. I know that sounds very, very, very exciting, but you can actually, physical chemists do that. They change and manipulate some reactions into other reactions using math. Do you need to know this for A-Chem, for A-level chem? Do you need to know this equation? The only thing you need to know is that at equilibrium, that entropy is no longer changing, and that's going to come into play later on in the lesson today for something that we do need to know, which is why I have the slide there. And they put an addendum, I believe, in the textbook about this that you can read. But again, this specific standard is not in the requirements for Cambridge. All right, let's take a look at a couple questions from the textbook before moving on. It says, decomposition of calcium carbonate does not take place at room temperature. What is the reaction for the decomposition of calcium carbonate? Do you have to know your thermal decompositions by heart for the next test? Yeah, right? So what would it be for CaCO3? Why we even did a lab with it.
CO.
CaO and CO2. So all carbonates decompose like this. They're called thermal decompositions. And it says, explain in entropy changes why heating calcium carbonate to a high temperature increases the likelihood of the reaction taking place. What do you think? Why do you think that as we reach the temperature, this reaction is more likely to take place? Go ahead.
It's because it's more energy to break bonds.
So you have more energy to cause the ion polarization to happen. Francesca?
Maybe the signal stability is higher, so it takes more energy.
Right, but why does it increase the likelihood in terms of entropy changes? Because the reaction is, the entropy factor is favored, right? So nature favors higher entropy. So although the reaction doesn't take place at room temperature, an input of energy does favor making the products because you're making gas. You're going from solid to gas. So nature favors higher entropy. So although the reaction doesn't take place at room temperature, at high temperature, the reaction is favored to occur. That's the machine. If any of you are doing STEM challenge, you may be working with a 3D printer later this year. If that's what you want to do.
Yeah, you can do it for numbers.
Because entropy increases. And specifically, more moles of gas product. So this isn't an actual Cambridge question, this is just an idea question, but I would get in there that you have more moles of gas product, which is why the entropy increases. So the idea, just rereading it back, nature favors higher entropy, so although the reaction doesn't take place at room temperature, at high temperature the reaction occurs because the entropy is increasing. So the entropy factor favors these products being made, but you need a high enough temperature for that reaction to begin. So this is an example of an endothermic reaction that at the end, the entropy factor at a high enough temperature wins out. What is that high enough temperature? That's what we're going to find out later on in the lesson. Because that's one of the things we need to know. Ready to continue? In a closed system at a high temperature, reactants and products are in equilibrium. What is a closed system? This is something that we did go over last class. What is a closed system? Go ahead.
Like a vacuum?
It's not exact. That's an isolated system. What is a closed system?
The one in which there's no loss of mass.
A
There's a loss of
system
energy.
in which there is no loss of mass. That is correct.
We say energy instead of mass, or does it have to be mass?
Isolated system is energy. So it is mass. The idea is that the chemical equilibrium is established because the container is not open. So if the container were to be open, then as A turns to B, B just goes away. The way that I think about it is always with water. If I have like a beaker or a cup that has water in it, and we leave one in this classroom, I mean, we could do that. No, hold on. Hold up. I mean, it's gonna be slow. It's not gonna be fascinating.
You did that?
Okay, I have 400 milliliters of water in the beaker.
Whoa!
It's not fascinating. Just let it sit there. Don't do anything to
So I
it.
could drink.
We'll be back to that in some weeks from now.
Actually, mix.
Yes.
3 weeks?
So what's going to happen with time is what? The water is actually going to evaporate.
Oh.
And for some reason, the evaporation rate at this school is pretty high, and I don't know why. In comparison to my old school, the evaporation rate is very high. So high that if I were on your lab exam to have prepared your reagents and poured your concentrations out for your titration the night before your Cambridge exam, it would alter your results.
Oh.
It would change the concentration enough because as water evaporates, it gets more concentrated. It would change your results enough to be off. And so that's actually why the reagents have to be poured fresh like within an hour of when it's going to be done. And then I have to have the same concentration that you all have. Make sense? Anyway, so the idea here is that in an open system, as any equilibrium is going on, here it would be the equilibrium between the liquid phase and the gas phase. If it's an open system, you've got molecules, water molecules here that are ready to just like spring out. The top ones get a little bit of extra energy and they start coming out. Why don't we see it?
And it's slow.
It's gas and it's slow. You're not able to observe it. It's not observable. The only observation is over time. You're going to see that that liquid level just starts decreasing. Okay, so a system in which there is no loss of mass is a closed system. In terms of entropy changes in a closed system, what happens when pressure is increased? So let's say that we had a system that you had a piston in. If you don't know what a piston is, basically it's like this, and you have that, and you can push it down. And let's say you have some gases here, right? Gases. What would happen if you were to increase the pressure on the system? You're pushing your gas molecules closer to each other. And if you're pushing your gas molecules closer to each other, that means there has to be less. Well, there's less volume. So there's less space for them to move. So there's less possible arrangements or positions of where those particles can be. So the place we get is to, because there is less volume as a result. As a result of increasing the pressure. There is less arrangements. There's less potential particle arrangements. And what does this mean for entropy? Yep. Which means there will be less entropy, or there will be decreased entropy. There will be less entropy. So that's the idea of what's going on there. This is considered a closed system where the mass is stuck in those areas. So you can use a piston with like a steel cylinder and then like raise it higher or bring it lower. When you bring it lower and you decrease the volume, you're actually increasing the pressure as a result. Yes.
Do you have any vacuums?
No. When I first switched from college to high school, that was actually one of my first complaints, is that we don't have a vacuum. Because filtration would be so much easier if you had a vacuum filter, because you would, be able to take out a lot of the water. So that can be future improvements, but money, it requires a lot of money. So, I'm starting to try to work on writing grants to get more equipment in the room, but it's something that takes a long time. All right, let's go ahead and continue. What is then Gibbs free energy? So far, we have reviewed what is delta H. We've talked a little bit about entropy. And so now we're ready to talk about Gibbs free energy. And so it's named Gibbs after a scientist. I do have an article from NIH, which is the National Institute of Health, that I'll share as a resource later on that talks a little bit about why Gibbs free energy is so important in biochemistry. Because there are certain reactions that shouldn't be favored that are favored. Like if you just looked at the enthalpy of the reaction, it wouldn't be favored, such as when you are looking at the production of ATP, which we use for energy. But with the delta G, not only is the enthalpy a factor, but also the entropy of the reaction is a factor. So you actually get what we call an energy payoff as a result of the reaction, which means that the reaction will still end up happening. And that's why we are all alive and functioning the way that we are. And so this is just there's some biochemistry. And if you are going to go into medicine and you are going to study biochemistry, Gibbs free energy is totally a big deal in biochemistry. It is looked at a lot. All right. So Gibbs free energy tells us if there will be enough energy available to do a chemical reaction, which means that it is actually the delta G itself that tells us whether a reaction will be spontaneous, which means it happens, or non-spontaneous, which means at this temperature, it does not happen. So spontaneous means what again? If a chemical reaction is spontaneous, how do we interpret that? The reaction occurs, right? The reaction occurs at this temperature. And if it's non-spontaneous, this means reaction does not happen at this temperature. So for example, if I were to set out a sample of calcium carbonate, like the white powder calcium carbonate, on a table, and I left it for years, it still wouldn't thermally decompose because at that temperature, it does not have enough energy for the thermal decomposition to happen. That's what we would call a non-spontaneous reaction. Spontaneity depends, as you can see here, on temperature. That's one of the factors. So we'll take a look now at the actual equation, and then we're going to get to the math on how to solve it. Because to me, this is actually a lot in terms of what you have to do with it, like the IC gas law, where you have equations, you have to plug in numbers, you have to solve it. And there'll be a few more when we get to Unit 3 that are just straight up equations that you gotta know. So this is it. Delta G is defined as the enthalpy of the system, which would be delta HR. So delta HR for all intents and purposes, minus T, what is T? Temperature, and then the delta S of the system as well. The delta H and the delta S will be given to you with room temperature values typically. But what is stated is that the enthalpy and the entropy don't change enough at different temperatures for you to have to manipulate and get full new tables of values. So you'll be able to use the standard enthalpy values provided to you and the standard entropy values provided to you in order to solve any questions. And find what's called the standard molar Gibbs free energy of formation. And so this is the energy change that accompanies, yes.
Because all these enthalpies that we have been seeing in the past in classes, they are given a standard.
You're given a standard.
Okay.
So like these are standard values, right?
If we were to try and see different enthalpies at different temperatures and pressure,
There's equations for that. There's equations for that, physical chem. So more advanced than this course, but yes, there could be, there will be at higher levels of study. And you can look in the book and they talk about these surroundings factors and how you can use the surroundings factors to help you predict the systems factors. But again, that's outside of what really is necessary for the syllabus, so that's why I'm not covering it. Go ahead, Adsel.
Is the T in Kelvin or what?
That's a great question. The T is in Kelvin, which is something that presents a possible source of confusion because the unit is Kelvin, right? What else is K? Equilibrium constant. And I don't know, maybe that's a reason they don't have you do that formula, but your temperature unit will be Kelvin. What will your units of delta HR be here on that note? What's the units of delta H? KJ, mole. And S has to be in KJ, mole minus 1, K minus 1. Those are your units of entropy. Why does it have to include the Kelvin? Because it actually cancels out with the temperatures Kelvin. And that's why last lesson, you actually should have seen, when we first introduced delta S, I just told you the units are joule, mole minus 1, K minus 1. It has to be because it has to cancel out the Kelvin. And then what would then your units of delta G be? What do you think? kJ mole minus 1. It's also kilojoules per mole. So it's the amount of energy you have for a reaction to happen. So it's a free energy change that accompanies for the standard molar Gibbs free energy the formation of 1 mole of compound from its elements in their standard state. I don't believe that I saw that as a standard you have to memorize. So I don't think you need to memorize that word for word definition because it's not in the standard, but I did provide it for you. Remember when you're studying for your test to look at the learning objectives in the front because that tells you what it is you actually need to memorize, do, follow the command words. All right, so then if you get a positive delta G, what this means is that at this time, at this temperature, the reaction doesn't happen. That it would require additional input of energy for the reaction to occur. And the reaction will be classified as non-spontaneous. And if delta G is negative, then what this means is that there's an excess, an abundance of energy available, which means that the reaction will happen. There's energy for it to happen, so it's going to happen. And so we call that reaction spontaneous. So the way to think about it is if delta G is positive, that's a no-go. No-go. And if delta G is negative, that means
That's good.
let's go. Reaction is happening. So we'll look at how we put delta H and delta S together to figure this out. But first, we're going to do some math. We're going to practice with the equation and see with the practice if we get reactions that occur or reactions that don't occur. So this is checkup 8 from the textbook coming up next. You've got the same S values as what you had last class. The same entropy values, standard entropy values, by the way. So it says calculate the standard Gibbs free energy, right now standard, in each of the following using the standard molar entropy values. What does standard mean? Standard what? Standard temperature and pressure. So they're asking you for delta G in the circle. That's what they're asking you for. And they're giving you S for the circle. That circle would be there, right? Molar entropy values. It says express your answer to 3 significant figures in kilojoules per mole. In each case, state whether the reaction will be spontaneous or not spontaneous under standard conditions. So here you've got the chart. I'm not exactly sure how it printed. You might have to be flipping back and forth with the pages. What I did was I had a screen that had this up, and then I had the actual map, but you'll have to flip back and forth. Or you could take the values from your last lesson. If you've got your notes from the last lesson, you could take out that handout to have the values to look at as we look through questions, because they're the same entropy values from last time, I believe. All right, so check up 8A. We're being asked to find delta G. First thing is to what? You have it. You have delta H. Delta H required. What else do you need? Well, sorry, I'm going to say, shouldn't we write the formula first? If we're being asked for delta G, we should know the formula. Sometimes, and it especially happens here in this area, if you could literally just write the formula, that's oftentimes 1 mark. So even if you get lost in the solving, you're like, they asked for Gibbs free energy. Delta G equals delta H minus T delta S. 1 mark. On a lot of the mark schemes, literally just identifying the right formula and writing it out for them is 1 mark. And that's what the state objective is. But then we have to have this stuff. We have the delta H. Do you agree? Do we have the temperature? Do we have the temperature? Look back at it again. What is standard temperature? It said standard. That's the key word. What is standard temp? They're expecting you to know that standard temperature is 25 degrees Celsius and that you know how to turn that into Kelvin. How do we change that to Kelvin?
At 273.
at 273, 298 Kelvin is your standard temperature. So we have temperature. So we've got delta H, we've got temperature. What do we still need?
Delta.
Delta S. So to find delta S. And that's what we learned how to do last class with these values. We were able to pick up these values for reactants in our products, do products minus reactants, and find what our delta S is. So what I did, and just see if you pick up the same numbers as me, I got 130.6 for my H2. I got 165 for my Cl2. On the other side, I got 2 times 186.8. So for my products, I got 373.6. For my reactants, when I added these together, I got 295.6. And then I found delta S, remember, is your products minus your reactants. So it's 373.6 minus 295.6. And it's 78. What? What? Units are going to be important here. Look at your chart. Joule, mole minus 1, K minus 1. Why are units important? What does G have to be in? KJ. What is your unit of S in right now? Joules. Will you be able to directly plug this number into that formula? Would you? That won't work, right? Because you have to combine, delta H is going to be in kilojoules. You have to combine it with another unit that's in kilojoules. The units have to match. Does that kind of make sense? So therefore, you now have to change joules to kilojoules. Another way I'm comparing this to the ideal gas law, because guess what? We're having to do conversions. How do I change joules to kilojoules? I'm going to go ahead and put out my little number line, right? King Henry died unusually drinking chocolate milk. And you're right, I'd tell you divide by 1,000, if that's the way you want to go about it. You move your decimal over 1, 2, 3 spots to the left. So you have to move this decimal at the end of the number 3 spots to the left, and that would give us what? Are we good? Does that make sense? I now have delta S. I have delta H. I have T. Can I solve the question? So 3, solve.
What does the K stand for again?
Delta G equals what?
What does the K stand for again? In delta
Kelvin.
Okay.
Kelvin. Let's write in the units this first example, just so you can see what I'm talking about. Generally speaking, when you solve these questions, you don't have to write in the units as long as you know that they all cancel. But let's just write them in for the first question, just so you understand how they cancel. So for delta H, we've got negative 184.6 kJ mole minus 1, right? Then it subtracts 298 Kelvin multiplied by 0.078 mole minus 1 kJ. I feel like I should say JK. KJ? Forgot to put the KJ in there. KJ mole minus 1, K minus 1. So what happens here? The K's cancel, right? Does that make sense to you? Or should I write that out further? Does it make sense that this K minus 1 cancels with this K to the positive 1?
Mm-hmm.
So then both of these are now in the unit of KJ mole minus 1. And if they're in the same unit, you can just add the numbers together. That's the idea. And so if this wasn't in kilojoules, you could just simply add these numbers together. So now that I've at least brought up what the units are, I'm going to drop them because I know they're the same. So negative 184.6 minus 298 multiplied by 0.078. That's what we did in our calculator. Delta G equals, try it yourself, see if you get the same number that I got. I solved these all yesterday. I got negative 207.8. KJ mole minus 1. Let me know if you get the same thing. Is this spontaneous or non-spontaneous?
Spontaneous?
Spontaneous. Meaning this reaction will happen at this temperature as listed.
I got negative 417.
So wait, how do you know if it's spontaneous or not?
Because the sign is delta G. If delta G is positive, it's a no-go, not spontaneous. If delta G is negative, it's spontaneous. So you will have to predict based on the sign of delta G whether this reaction is going to happen or not. This reaction would happen at this temperature. All right. Let me check yours. 0.078. You're missing one.
Oh, okay.
1 0. There's a 0 and that's definitely what it is. All right, ready for a second one? We'll do a second one together. The third one's your turn. Move on to the next one. Yes? All right, same steps. First thing, write your formula. So delta G equals delta H minus T delta S. Get in the habit, if you haven't been, write your formula before starting. Remember I said Cambridge often gives a mark for just writing your formula. So write the formula you're going to use before starting to plug your numbers in. Temperature is still 298 Kelvin because we are still in the same question, just the second checkup. And then how we find delta S.
Product times reactants.
Products minus reactants, right? So it's the standard entropy values of your product minus the standard entropy values of your reactant. So then I just find my numbers. This is maybe the hardest part because you have to make sure you pull the right numbers and don't confuse yourself. 186.2 plus 2 times 205. On the other side, I've got 213.6 plus 2 times 188.8. And I get 591.2 on this side. And on the other side, I get 596.2. So I get 591.2 minus 596.2. You'll notice what I like to do is add up my products and add up my reactants first before putting them in the formula. My reasoning behind doing that is because if you have multiple reactants like you do here, and instead you plug in all the numbers like this, if you had done instead, let's say 213.6 plus 188.8 minus 186.2 plus 2 times 205. What is the issue algebraically where you might mess up if you do this? Because a lot of people mess up when they plug in their products minus their reactants like this. I will say over half of my students mess up when they do it like this. What's the issue? You forget to distribute the negative. So like this is a -1 there. And if you plug in all the numbers and you put in all your reactants here, you have to remember that that negative would distribute. So in order to kind of have you not forget that, that's why I combine my products first and I combine my reactants first, and then I'm just subtracting 2 numbers. So that issue with distribution doesn't become an issue. But if your algebra skills are strong, then you can literally just do it like this. Like all your products and then subtract all of your reactants. Just be careful because you would be distributing a negative. All right, so delta S is then -5. What's the unit? J. Don't ask me why, because I don't have an answer for why delta S values are always given in joules and not kilojoules. But I'm going to tell you that delta S values are always provided to you in joules and not kilojoules, which means what? You're always going to have to convert to match delta H.
So first and kilojoules would be a small decimal.
It'd be a very small decimal, so maybe it's that they don't want to add decimal numbers. They're like, yes, numbers bigger than 1. I'm like, numbers bigger than 1, because when we change this, this is now going to be delta S is -0.005 joules mole -1 K -1. So you've got to convert it to kilojoules before you plug it into the delta G equation, or else you're going to get the answer wrong. So always convert joules to kilojoules. Are we okay with that? Which is always moving 3 spots to the left, because it's the same strategy as last time. Rinse, wash, repeat. Now what? Solve. We've got everything we need. Delta G equals delta H minus T delta S. I'm just rewriting it out. Delta H is -890.3. If I've already ensured my units are correct, do I have to write them all in? No. If it ends up being confusing to you to write them all in, then don't. Until the end. You have to write the correct units at the end. So minus the temperature 298, delta S is -0.005. And then when I solved this, I got, and check to see if you get the same thing, -891.8 kJ mole -1. Then the reaction is this spontaneous? The question is this spontaneous? Actually, I think it's not this, because I'm looking at mine and I see a sign error. Yes, that sounds right. In my way too fancy calculator. We were required to have these in college for some reason. -888.8. Did you get that? Try that again. Okay. So spontaneous or not spontaneous? Spontaneous. This reaction is what? What is this reaction?
Very likely to happen.
What is this reaction though? This is a methane. This is lighted on fire. Does methane gas light on fire? You just need a little spark, right? It's extremely flammable, extremely combustible, and yes, extremely likely to happen. So spontaneous means at that temperature, it can and does happen. All right, your turn. Try this one. So your turn means same strategy. You're trying to find delta G. Tell me if this reaction happens or not, and if it is spontaneous or non-spontaneous. If you try this one, I'm going to give you 5 minutes and check. I'll check it. Then we have one more thing to go over, one more major thing to go over. And we have, ooh, Cambridge question for the rest after this one. All paper 4 questions after this. You're so excited, right? All right, so once you have the answer, raise your hand and I'll tell you if you got it right or not. And I have a stamp. Are you gonna try it? Raise your hand when you're ready for me to evaluate your work.
Yes, I think I messed up somewhere.
I think you messed up.
I don't believe it.
And you have to tell me whether that is spontaneous or non-spontaneous. And while you're waiting, think about why that is spontaneous.
Wait, what?
While you're waiting. Yeah. This is not the final answer. Reevaluate your math again. This is correct.
You have this?
Daniel, I think that you inverted two numbers. Because it shouldn't be 6, 7. It should be 7, 6. But I don't know how that happened. Try your math again.
Wait.
I even rolled my eyes as I heard her say that out loud. Section. Another minute before I continue.
Yes, because it's supposed to be.
Very good. Very good.
Yes.
I don't know what I did.
Let me see. Okay.
Check
Let me
your
see.
math. You must have written in a wrong number or something. Because everybody else has 447.6. Why? So how did you come up with that? I feel like that's,
Let me check.
that's an infection.
Let me check your.
I got my.
Calculators really have to get it further.
Okay. Let me see it. Tabulate.
Raise your hand when you're ready for me to chat.
Let's go here, right? What do you do here? Oh, okay. Minus. It is lighting on fire.
No.
Oh, this one.
Oh, I don't. Oxidation. It's 5.9.
Oh, there's no
All
fact.
right, at this time, I'm gonna go ahead and give the answer and then move on.
I don't like, I did the whole thing.
All right, so I'm just gonna put how to get the answer. If you didn't get it, it was 2 times 51.2 plus 1 plus 205 on this side, and then on this side it was 95. And then when you subtract those, you get negative 510. Well, this is I don't even know looking at my work. 95 minus 307.4 is negative 212.4. Which is the joules, which then has to be translated into here. Minus 298 times 0.2124. And then delta G is negative 447.6 kJ mole minus 1, which is indeed spontaneous. And then I asked for anybody who finished early, think about why this ends up being spontaneous.
Sodium
Axel?
Wait, sorry, I had a question. Why did you ignore the 0.9?
Ignore the what?
The zero, like.
If you don't put the 0.9, that's how you get what I got.
0.9?
It's 510.9. That's why I had my thing wrong.
Oh, I probably plugged it in the calculator correct. Negative 510.9. I just forgot to write the 9
That's
on
what
there,
gives you-
but I have it here.
Wait, what did he get?
I got negative 447.6. That is what it is.
I got negative 448.67.
Try this again. Negative 510.9 minus 298 times negative 0.212.
That is literally exactly what I did.
Can I go or should you come?
You look at your calculator?
These two should multiply together, and then they got positive, right?
Wait, why do you have a 5 times 0.9? Oh, no, that's 5 times 0.9. And then these two should multiply together. Did you put 293 instead of 298 maybe? Because I don't see what you put in your calculator.
Oh, no.
98, 298, 298. That's what it is, 8, not 3. All right, so think about what's going on here. This is forming an ionic lattice. What did we say about that lattice enthalpy? It was going to be very exothermic, meaning that there's a lot of energy released to put an ionic compound together. Do you think that's favorable or not favorable? Exothermic reactions are very favorable to occur. But look at the entropy. Does the entropy tell us that this would have been a favorable or a not favorable process? Nature favors what? More entropy, right? So this is going from more entropy to less entropy. So entropy tells us, if we were only looking at entropy, that this reaction would not be favorable. What is the reaction at the end? Very favorable. So which factor is more important in this case? The enthalpy or the entropy? The enthalpy. The lattice enthalpy being very exothermic overcomes the idea that you're going from a gas to a solid. And so that's what I'm saying, is that there's going to be an interplay of the two factors. And that's where we're going to see changes in temperature come into play. Like at certain temperatures, the reaction will be favorable. At certain certain temperatures, the reaction won't be favorable. So that is going to be our last topic. Yes.
Well, we have to make an analysis of negatives or negatives again, like the hydration of sulfate.
It won't be as complicated. I don't think it'll be as complicated, but maybe.
Okay. Well,
Maybe it will be, because it is a subtraction. Delta G minus T, delta S, where delta S is negative. All right, so let's take a look at paper 4 question. Calculate the standard entropy change. They're giving you silver chloride. They're telling you it's sparingly soluble. And then here's the enthalpy change of solution. If you'll recall from that lesson, that enthalpy of solution is telling us that this isn't very likely to dissolve very much. Because remember, the more positive, the more unlikely to happen. That's because this is endothermic, meaning there's a requirement of energy for this to happen. So the question is entropy a factor that can outweigh the enthalpy of the reaction not being favorable? And so first, find the standard entropy change of solution. How do we find that? Delta S is products minus reactants, right? So products minus reactants. Here, the numbers are about as easy as they can be because you only have one of each thing. You have 2 products and 1 reactant. So 72.7, 56.5, 96.2. If we add our 2 products together, we get, did this math earlier? Actually, no, I didn't. I just plugged it all in my calculator at once. I did 72.7 plus 56.5 minus 96.2, because there's only one thing to subtract. And I got positive 33. What do you think about that entropy? Is that positive or negative? Yeah. You should. This is positive entropy, isn't it? which means that the entropy factor says that this is favorable. It is favorable for this dissolution to happen. But the enthalpy factor says that this is not favorable. So the question is, which one wins out? They're telling you, explain why the aid of calculation, they're telling you HCl is insoluble, meaning that it's not going to dissolve. How can you prove it? How can you prove that this is not going to dissolve? Enthalpy says it won't. Entropy says it will. How do you know if it wins out?
Please.
Go ahead, Francesca.
I'm not sure. The enthalpy change of solution.
That's not the only thing. Isa,
Using Gibbs free equation.
you must use Gibbs free energy. So they say explain with the aid of a calculation. They're asking you to get to, oh, I've got the entropy factor and I've got the enthalpy factor. I'm going to need to combine the two together. So I'm going to need to use Gibbs free energy, which is what they give you this space for. So delta G equals delta H minus T delta F. Delta H is 65.5. That's the enthalpy of solution. What's the temperature? It's standard, so 25 plus 273, which is 298. And the delta F is what? I'm just in the habit of moving my decimal over 3 spots every time. So in my work, I just wrote 0.033. Does that make sense to you? Delta F must always be changed from joules to kilojoules. So then I did that math. And when I did that math, I came up with positive 55.6 kilojoules mole minus 1. Okay. I don't know. Now I'm gonna cry. I'm gonna go home. Bye. Everybody. Why? Let me see. It's 65.5 minus 298 times 0.033. It's 67.
6, 7.
So, yes. Must mean Kelvin.
Why don't we use bearing something on the soluble?
I don't know why they changed the words this time. Whoever that governing panel of people in, I think it was November 2023 that made this question, decided to use the word insoluble, so give them a little pow-pow. Because they should have used sparingly soluble, right?
Imagine like on the accent credit tab, you like cross it out and put sparingly soluble.
For the examiner. I mean, I don't know. All right, so
That could be a question that like give the marks because they say soluble, reality is sparingly soluble.
insoluble, as what we used to know it as, is now sparingly soluble. So they're assuming you know. They're just trying to say, hey, y'all, this don't happen. That's literally why they're using that, is to make it definitive that this is not going to appreciably dissolve in water. Why? Because the delta G is positive. How do we explain that? How do we explain it? Because there's explain with the aid of a calculation. So we've got the calculation. You still have a mark on explanation. What do you have to say? Because delta G is positive, the reaction is not spontaneous. That's all you have to say. That's your explanation. If delta G is positive, the reaction is not, and I don't know what happened here, spontaneous. Not spontaneous. That's all. All right, we have one more standard to get through.
Oh.
The math proves it. Literally 1 mark for the equation. A lot of people would not come up with the equation that they need to figure out because they're not telling you have to use delta G. You have to come up with that. You have to use delta G to figure this out. What is your clue? They've provided you delta H and they provided you with delta X. So that's your clue. You have to use delta G. All right. Last topic for the day. Last standard. how do we predict at what temperature a reaction will turn from spontaneous to non-spontaneous? That's the last topic. So temperature and reaction spontaneity. In order to predict how temperature will affect how spontaneous a reaction is, we have to consider two things. Does nature favor the process for enthalpy, and does nature favor the process for entropy? So what does nature favor? Like, what is favorable for delta H? What does it favor? Exothermic or endothermic? Exothermic, right? Nature favors delta H to be exothermic. What does nature favor entropy to be? Like, delta S is favored because of second law of thermodynamics to always be increasing. So delta S is favored to be hot. And so if you were provided a delta H value that's negative and a delta S value that's positive, the reaction always happens. I mean, as long as we're above 0 Kelvin, I guess. Even then, theoretically. So if delta H is negative, delta S is positive, there is nothing you can do to change the temperature to change whether the reaction will be spontaneous or non-spontaneous. That reaction is going to happen. So what if we flipped things? What if we said that delta H was endothermic, so not favored, not favorable, and delta S was negative, meaning less entropy, also not favored? Would this reaction happen if both factors are unfavorable? If this says it don't happen and this says it don't happen, will it happen? Will never happen. You can heat that reaction to 10,000 Kelvin and it still won't happen. If both factors are saying this is gonna not happen. So if the signs are opposite of delta H and delta S, that either means that the reaction's always happening or it's never happening. That's a way to keep it straight. If the signs are the same, like if delta H is negative and delta S is negative, that means you have competing factors. So if I say that delta H is negative, that's favored, and delta S is negative, that's not favored, that means there will be a temperature range where this reaction will happen, and there will be a temperature range where this reaction won't happen. Yes?
Are there any exceptions to it never happening?
Not that I know of.
Good.
not that I know of. So if delta H is positive, is that favorable?
No.
No, not favored. But if delta S is positive, is that favored? That means there will be a range of temperatures where this reaction will happen and a range of temperatures where this reaction will not happen. And so that means that the T factor, the Kelvin factor, comes into play. Go ahead, Isa.
So the question is, does this only apply to chemical changes or
All systems,
or systems?
all systems, all thermodynamics. All right, continue. Given this idea, let's look at a basic question. Spontaneity at different temperatures. Basic question, then I give you this reaction. Ignore the complexity of the reaction itself. This is our unit 4. It's ethane dioate. And they shorten it by calling it PN. This is actually a metal complex. We're going to learn about these in unit 4 when we get to transition metal chemistry.
It's actually.
We're going to learn about metal complexes. These are called ligands right here. This is a bidentate ligand. That may not make any kind of sense, but this reaction happens. So all you see is, hey, reaction. Notice I isolated this. There's a lot more to the question, and I just basically isolated the part that you needed. I have to be very careful when writing my exam questions for this reason, to make sure that I'm only giving you the part that's relevant to what we've learned so far. Because remember, at the end of the year, they combine all of the standards, together. So that's why you'll see unit 2 questions in unit 4 sometimes. All right, so here we go. This is the reaction. These are my delta H and my delta S values. Notice the sign is the same. Notice to me, this is a very small delta H value. Do you see that? This is a very small endothermic value. So that means that the entropy factor is definitely going to be one that can overcome the enthalpy factor. And so they tell you to calculate the value of Gibbs free energy for this. So this is equilibrium 4 at 298. For 2 marks, can we do that?
Yes.
2 marks? I feel like 1 mark. There's some other 2-mark questions that are much more difficult. Remember the whole Bornhaber labeling of the whole entire cycle? Also worth 2 marks in this unit. All right, so delta H is 0.840. Temperature is 298. And delta S is what? They gave it to us in joules. What does that mean we got to do? Divide by 1,000 or move it over 3 spots, and so that it's in kilojoules. So we do this, and we get delta G is, I get negative 23.3. How many of you get the same? How many of you get the same? Before I even talk about part 3, is this spontaneous? That means at room temperature, because 25 degrees Celsius is a little bit more than room temperature. It's when I did the lab exam the other day, the temperature said was in the room is 23 degrees Celsius in here right now. So just a couple degrees above what this room is in Celsius. So 23.3, a little bit above room temperature, but it's called standard temperature, or our room temperature. Is this spontaneous? This is going to happen. But enthalpy says it wasn't going to happen because entropy is the outweighing factor here. So this is spontaneous at this temperature. The next question, 4 mark, state how the value of delta G changes as the temperature increases. That's also state and explain. Safe to say why. So what would happen to the value of delta G as the temperature continues to increase, Issa? It decreases. And that is where the math is. This is positive, right? This is a negative times a positive, which means that this is negative, because negative times positive is negative. So as this number goes up, the 298 goes up. That means the negative factor is increasing. If the negative factor is increasing, where the positive value stays the same, that means that delta G is going to become more negative. So the way that they say the answer is more negative. That's the state. And then you could say one of 2 things. I would say as T delta S increases, that factor increases. That factor increases. This factor increases with increasing temperature. You could have also said, if you don't want to say it that way, or they also accepted more negative. So I'm giving or, whichever one fits with how your brain works better. More negative as delta S itself is positive. Because delta S is positive, that means this factor will end up being negative, which means that delta G will become more negative as you increase the temperature. But they expect you to say one of these 2. What? One more question?
One more game for tweaking.
Oh. Yeah. One more slide, then we'll talk about that decision you have to make.
What is it?
I mentioned at the beginning of class, some people caught what I said, some people didn't. Some
Some
people may not have been here, some people might be tired, but you have a decision to make shortly. All right, so last question for the day. Lead-4 oxide, it's your turn. Decompose to the lead-2 oxide, PBO, and oxygen when heated. They give you this, they ask you to find the delta S. I'm going to help you out with this one. because I did say it's your turn. It says use the value of delta H in your answer to A to calculate the temperature at which this reaction becomes feasible. So just to help you out, for a reaction to cross from not happening to happening, where would you cross delta G at? What number would delta G have to be?
Here.
So this actually means set delta G equal to 0, and you'll find what temperature the reaction goes from spontaneous to non-spontaneous or feasible to not feasible. Here from not feasible to feasible. So go ahead and try this one on your own. This is your last question. I want you to try it yourself first, and then I will go over the answers.
What is lock in?
Yep, lock in. And then we'll go over that one thing that I gotta tell you.
I've already voted.
You already voted?
Where's this more savage?
Why do you divide by why? You don't need to, right?
You'll
Like,
be-
you go
That must be a bike because I'm too tired.
Am I what?
That must be a bike because I'm too tired.
Oh, I get it. Too tired, too tired. That's crazy.
I think I did.
I actually woke up with tons of energy today, and I don't know how.
Yeah, me too.
It was neat. Surprisingly, I didn't have to go to home school. So after the woman, I went back home and slept for 10 hours straight and woke up at 7 p.m.
That might actually be the reason I did sleep 10 hours, like Wednesday night.
And I woke up for like 3 hours and then went back to sleep.
Why so serious?
All right, I'm starting to solve the first one. See if you get the same thing. For delta S, I got 189. Check to see if you got 189 for delta S.
Like 6.
And now I'm going to solve the second one. I'll give you a couple minutes first, but that is the equation.
No, you don't, because they only have 1K.
If we figure out how to find S, can we just write a random number for delta S?
And get an error carried forward, yes.
So if we forget
I would be careful about forgetting to sign with all of these, for delta G, delta S, delta A. I would include my sign always.
is there a way that delta S?
Oh wait, no, I did it wrong.
That is a great physics question because we've been diving into 2.4. The way for delta S to be 0 would be
I want to get that instead for my
right?
Here,
You can approach 0.
No, like delta S is the change, so it would just be a.
Oh,
What do you get?
I mean S itself to be 0. Delta S can be 0, yes. Yes, it can.
Miss, I don't know if this is right.
It just means that there's no overall change in entropy.
So if I put 0 in the calculation for delta S because I forgot how to calculate it, then error carried forward is just.
I don't know about that because it's only worth 3 marks. I think you get the point for the equation.
You know,
It's not
it was
negative
predicted by
6.4.
why 6 point design.
Yeah.
624.
Because 789.
Hey, you got
All right, I'm going to go ahead and put up the answer. 0 equals 118
Also,
minus T. Delta S
the
is
789
0.189.
is like keep
If you get this wrong, it may be your algebra. Subtract both sides by 118.
Daniel.
You've got a negative divided by a negative. What does that mean?
Positive.
That your final answer should be
Positive.
positive. So if you got negative 624, that means you forgot to divide a negative by a negative. But if you say negative 624 Kelvin, please think about what you said. 0 Kelvin is the lowest temperature that exists.
Yeah, you're right.
Just think about it when you're working through your text, okay?
But if
Like,
zero
think about
Kelvin is
your-
where there's no movement,
Negative.
negative Kelvin would be negative.
And that would make the reaction happen? That's the temperature at which the reaction would occur?
Negative movement.
All right, so let's talk about the decision you have to make.
Is there a place on earth that is 0 Kelvin?
Now, in a lab, it's a zero circuit.
The sentence.
Wait, so that they can't get to
The
0?
sentence.
All right, class votes. You have till tonight, and then I'll post it on Sunday what the class voted for. Currently on schedule. Your Unit 2 exam is on October 9th. That would give you 1 day next class to review, and then your Unit 2 exam would be the following class period next week on Thursday. That's what's currently on schedule, and your quarterly exam would be on October 22nd, which is after the quarter ends. And so the quarterly exam would fall into quarter 2. Therefore, you could not use the quarterly exam to replace your first unit exam. The only way you can raise your first unit exam if you didn't do well on it is to use your summer packet if you turned that in, or if you mess up on unit 2 exam. Turning your summer packet would be the only way to raise your grade. So that's option 1. In choice 1, there will be 1 review date for the unit 2 exam. We'll continue into unit 3 starting on October 13th. Quarterly exam would be on October 22nd. You will have a day of review on October 17th for the quarterly exam. You'd be given practice questions that day. Choice 2, we review all of next week. So we review next week on Tuesday and Thursday. So more review activities. But you will have a merged Unit 2 exam with your quarterly exam, meaning you just have the quarterly exam on Unit 1 and Unit 2 together, which means Unit 1 questions will be included. This would happen on October 13th, so that it is before the end of the quarter. And your new content for Unit 3 would then begin on October 15th. Having the quarterly exam before the quarter would allow you to drop your lowest score on the Unit 1 exam, or the, just the Unit 1 exam, for the quarterly exam. So quarterly exam grade conversion, if you'll recall, is, I saw those votes coming in. You can see it on there. I don't have it live for you. Yes.
I don't know which is.
All right. You have the night.
Poorly
Hold on.
edited to it. For you. Like it's oh, there's that music one biggest thing.
Why is
I forgot.
it?
Yeah, it's option.
What? What do you like to
Wait, it's 2 like choice 2 like a large exam.
Chapter 2.
Choice 2 is a larger exam.
It's again pretty long.
A full class October 13th quarterly exam that covers both Unit 1 and Unit 2. But
Oh, yeah,
you have the weekend to study and you have a full week of review activities. I've heard that there's also an ACE math set of tests for A level happening next week. On which day? On Friday. So for those of you in that class, Thursday, Friday would be back-to-back exams, or it would be Friday, Monday, where you have the weekend in between. So the vote is a class vote. 12 have turned in their votes. 15 still have yet to turn in. You have till tonight to decide. That's when I'm closing the vote. No, I just put tonight, like end of night. So pick your choice. Whatever the class decides is what I'll organize and make
Take
my
your choice,
lessons
then.
and reviews on. There's benefits and drawbacks to both for me as well, but I'm gonna give you the thoughts.
It was left.
This would be after Martin P. So it should be choice what?
I'm going to that end, but I'm only picking the 3 days. For the meeting.
I think there's
It's just better than.
wait, what's the about?
Yes.
Next week.
Sad.
Okay.
Yeah, I'm not doing it. Choice two?
Yes.
So this is choice two, choice two. Next week.
It's not a. That's fine. Yeah.
What do you guys vote for?
Option two.
Yeah, option three.
You don't know? Like you.
I said option two because it's after the map.
Yes.
I did not know.
I'm back.
Right.
Right now, the vote is choice 1 at 5, choice 2 at 11. Remember, you have till tonight to decide. Yes. Hold on.
Maybe never came in. Where's he? Like, okay.
What is that? What?
Listen, all you need to know is pH. It's like, I didn't say log. Why? What's the pH point? Negative. Okay, how do you do that? I was about to say negative acids. Say it.
Yeah.
Well, I'd be scared. I can do it.
pKa, right? pKa
Yeah, just
No. Okay. So for weekend, right? The thing is, basically, you need pKa minus log of sulfur acid. Obviously, pKa. I mean, like pH. Acid pH.
It wasn't a bribe, it was a piece of fruit. I'm still gonna cut it. It was a piece of it. It's a bribe, right? A piece of it.
But if you do your math right,
Not first. Like,
Oh, yeah. I did it.
I've seen that on a few people. I think that's what happens.
Oh, yeah.
All right, 21 people have voted. 21 people have voted. Right now, choice 2 is winning.
How many people are in the class?
Yes.
I think we're doing option 2, Daniel. Don't worry. Yeah, I know. It probably is. Like, people are too
I heard the person that I did not. I think they might have started after I left. I had some really good professors in FIU, stuff that were, but no, I don't.
What's the use last night?
I don't know if that's a good or bad thing, but I definitely heard the name of
Maybe you one.
If you have a good teacher, you're gonna have a good time. If you have a bad teacher, you're gonna have a bad time. And even if you're a good student, we don't need to be better than this. Because that would be on. And so I would always try to pick professors that I could talk about, that I could and their tests. That was just things that I learned about. Like I don't mind when I was hard as long as they adequately prepared me. Because
All right, Daniel, remember, these are some big ones that you memorize, right?
that it's over the
Unit 2, I think. You chose option 2, I imagine.
Yeah.
So you got stuff like each class plus 8 souls, getting into the integration, the cation, and
That's the two things that I always.
because you have a table over there where you take the aqueous ions, solid ionic compound. You could make that, you could do the alkaline solution, you get that to the aqueous one,
Not to context.
or you could do hydration of the two
Like,
ions to
or
get
you said- For the school.
We appreciate the time and effort you put into your application. It was like fun.
Like you all.
I think that
I think that's.
obviously too light in the
That's their.
that's your
Hopefully, there's a non-secret
That's
organization.
the professor. I just.
yeah, basically it's a
Standard
one
station.
one mole of gaseous phase element understood solution.
The people that I took, I probably a lot of them. They were all like older gentlemen who got their degrees in like the 1970s. So a few of them may be around, but a lot of them are probably retired. Yes.
So let's say for atomization you have 1/2 Cl solid. Wouldn't it just be
No, 1/2 Cl solid. Fluorine is a gas.
yeah, because one
Fluorine is so gas. So gas it dangerous. So gas, you know, it
you're right.
it mustard gas.
Just add in 1/2.
Yes.
What's like the percentage on the quarterly? Like the breakdown, unit 1 to 2 ratio.
Probably I have to count the standards and then do the breakdown. How many standards are from unit 1? So you can count the learning objectives. I can do that over the weekend, but you can count the learning objectives for each one and then divide them, and that's how you'll know. Yes.
Can I see what the acceptance letter for SNHS is? Because we did this for Alpha Theta, but I don't like what Dario wrote. I don't know. It feels a little goofy because he wrote like non-secret organization. I don't know. It just doesn't feel.
Oh yeah, I would take that out.
You can zoom in if you want.
Like a minimum was like
Overall, looks pretty good. Probably more detailed than mine.
I designed it, but
Yeah, I'm not sending mine out yet.
I'll talk to Morales.
Have Morales definitely look it over. Don't send that out without Morales, but get rid of the non-secret, those words. Yeah, get rid of those. Yes, ma'am. What's up? We're having a good weekend. We're gonna.
Well, okay. So I was supposed to take the SAT on Saturday, right?
Oh, so not a good weekend.
And so then I asked Miss Kaufman because when I check on the website, it says I'm taking it on Saturday, but it says the location's at school.
What?
Yeah, so I'm like,
Ain't nobody
that's
coming
not
here.
right.
I don't think
That's
right.
not right. So I emailed her asking her, hey, what's the location? Do you have a different location? Because
Yeah,
my thing says this. And then that's when she tells me that no, they moved my SAT to Tuesday for my accommodations.
Oh. So one of our review days
Which is
during school.
yeah.
Who else has October 7th SAT?
But like, why would they
Because I heard a bunch of seniors are.
today? And if I wouldn't have asked her,
You wouldn't have known.
I wouldn't have
You would've
known.
came to the school.
And then I would have came to the school. I planned yesterday all around that. Tomorrow I have a birthday party. Huh? No, but then here's the cherry. Here's the cherry. And then I'm like, I want to say 5 minutes later, after I send the email, she sends this email to cover herself. After I already asked her. So she sent this to cover herself. Who do you think? Sorry, that was. Like, lady.
I definitely feel your stress.
Hey.
And then she's messed up my accommodation so many times that was like it probably would have been better if I do it on Saturday. Because of how many times she's messed up. Last year was the only year that she has not messed up my accommodations.
For the Cambridge exams or
For
for the
anything.
regular testing?
For anything. For anything.
So you have to be vigilant.
Yes.
And make
For the
sure
ACT,
that you.
you had your accommodations for the ACT.
ACT? Yeah.
Yeah.
It wasn't here.
Mm.
And then I had to fight her to get me the paper
For
so I
the
can give
reader?
it a Fleischer so that way I can give it to them so I can have it.
I'm sorry.
Like,
It
why?
sounds-
Like, so now
Hey,
today
Sabrina,
is-
you're here. I'm gonna need you here.
Yeah, you tell me.
She's getting it out. She's getting it out.
You couldn't tell me the day before.
Bye. Have a nice weekend. Well, at least I guess you get time. I'll be right back. All right, don't forget to have homework to turn in today. There should be 2. Good morning. Good morning. And then go ahead and get signed in for that bell word. Got to complete a part Tuesday. Good morning. Good morning. Happy Friday. Good morning.
Oh.
Alrighty, good morning. I'm so happy to see you all. I missed you all on Tuesday. I was here, but I was preparing for a lab examination that took place during your class. So we are moving right on forward today to lesson 2. That means today you're going to practice lesson 1 for your bell work. You should have your notes out. Make sure you write your name on your homework and turn it in. Vermont, I don't see your name on there. Make sure you write your name on your homework and turn it in. You should have both the homework and the work that you did with the substitute on Tuesday, which was just a few questions on Bohr models, finding the simple electron arrangements. And then you had also had an Edpuzzle, but obviously that was done digitally. So you've got about 5 minutes as always to organize, get ready, and we'll get started real shortly with the first activity, which is your bell word. Let me check. We're missing Rebecca today and Amber. Oh, and we're missing 4 people from period 5.
You bring the media too?
Yes. Some people were turning it in.
I get that.
Okay, so I'll pick it up during lunch and give it to you after lunch. Yes.
I wasn't here on Friday, so.
That's right. So you need that lesson note and you need the homework. Were you able to catch up on the lesson at home or no? Okay.
I didn't pick it.
So if you want, you can try the lower. If you have those notes out from last class, this is a lot of questions you can help with last class. And then this is the one from last class I was here with last Friday.
You just got this?
All right, so we've got about 3.5 minutes before we get started. We're doing part 2 today, which is the really big part. In my B days, which are now ahead of you all because I wasn't here on Tuesday, they found the lesson to be pretty good, like much better than the first lesson. So that's what you can tend to expect is that by the end of today's lesson, you'll be way more clear on what it is you actually need to be doing. All right, so 3 more minutes till we get started.
This one's staging.
Okay, we can bring it to you.